everyone, welcome to our video lesson. Today we are going to talk about something very important in electronics, the operational amplifier, also known as an OP-AMP.
And specifically, we will focus on one of the most classic devices, the LM741 operational amplifier. In this video, we will explain what an OP-AMP is, how it works, and most importantly, we will analyze its performance parameters based on the datasheet.
We will also include simulations to verify some of these parameters.
So, what is an OP-AMP? An operational amplifier is a device that amplifies voltage.
It has two inputs, the positive input and the negative input.
And it amplifies the difference between them.
In simple words, output equals gain times the difference of inputs.
In an ideal OP-AMP, the gain is infinite, input resistance is infinite, and output resistance is zero.
But in real life, this is not true. Now, before we continue, I want to talk about in detail of the LM741 operational amplifier. This device is one of the most important in analog electronics. The LM741 is a general purpose operational amplifier. This means it can be used in many different applications. For example, signal amplification, filters, comparators, and even mathematical operations. It is widely used specifically in education because it is simple, reliable, and easy to understand. The LM741 is an integrated circuit. This means that all its internal components like transistors, resistors, and capacitors are inside in a single chip. This makes that the device compact and practical. Inside the LM741, there are three main stages. First, the input stage. This stage receives the signals and compares both inputs. Second, the gain stage. This is where most of the amplifications occurs. And finally, the output stage. This stage delivers the signal to the external circuit. Another important characteristic is that the LM741 this is a differential amplifier. This means that it does not amplify just one signal, it amplifies the difference between two input voltage. That is why it has two inputs, the not inverting input and the inverting input. The LM741 also requires a dual power supply, and in most cases we use positive and negative voltage. For example, plus 15 volts and minus 15 volts. This allows the output to move in both directions, positive and negative. Another important feature is that the LM741 includes internal protection. For example, it has overload protection and it avoids unstable conditions like latch up. This makes it a safe option for experiments and learning. However, it is important to understand that the LM741 is not perfect. Compared to modern OP-AMPs, it has some limitations. For example, it is slower, it consumes more power, and it cannot operate with very long voltage. Even with these limitations, the LM741 is still very useful, specifically for students and basic circuit design, because it helps us to understand how real OP-AMPs behave. Another reason Why this device is important is that many modern amplifiers are based on similar principles. So by learning the LM741, we build a strong foundation. In summary, the LM741 is an educational operational amplifier. It allows users to study the fundamentals of analog electronics and understand how amplification works in real systems. Now that we understand the device, we can start analyzing its performance parameters.
The LM741 is a general-purpose OP-AMP.
It's very common in electronics labs.
Now let's analyze its parameters.
First, offset voltage.
This is a small error in the input.
Even if the input is 0, the output may not be 0.
Typical value is about 1 millivolt.
Maximum is about 5 millivolts.
And now let's talk about power consumption.
The LM741 uses about 1.7 milliamps.
And maximum is about 2.8 milliamps.
Power consumption is around 50 milliwatts.
Now let's talk about CMRR.
CMRR means common mode rejection radio.
This parameter is very important because it tells us how well the OP-AMP rejects noise.
Specifically, noise that appears equally in both inputs.
For example, imagine both inputs receive the same interference signal.
In an ideal OP-AMP, that signal should have no effect on the output.
But because the OP-AMP only amplifies the difference between the inputs.
But in real life, some of that noise still appears at the output.
That's why we use CMRR to measure how good the rejection is.
A higher CMRR means better noise rejection.
For the LM741, the typical value is about 95 decibels.
And the minimum value is around 18 decibels. Now let's move to PSRR.
PSRR means power supply rejection radio.
This parameter measures how sensitive the output is to change in the power supply.
In real circuits, the power supply is never perfect.
There can be fluctuations, noise, or ripple.
If the OP-AMP is sensitive, those variations will appear in the output.
But a good OP-AMP reduces that effect.
That is exactly what PSRR measures.
For the LM741, the typical PSRR is about 96 decibels.
And the minimum value is about 86 decibels.
Again, higher is the better.
So, a high PSRR means the circuit is more stable. Now, let's talk about gain.
Gain is one of the most important parameters.
It tells us how much this input signal is amplified.
In the LM741, the open loop gain is very high.
Typically around 200,000.
This means a very small input difference produces a large output voltage.
However, this gain is too large to use directly.
That's why we use feedback to control the gain.
In practical circuits, we work with closed loop gain.
But the high open loop gain is still very important
because it allows accurate amplification.
Now, supply voltage range.
This tells us what voltage we can use to power the OP-AMP.
The LM741 typically works with plus minus 15 volts.
But it can operate with plus minus 10 to plus minus 22 volts.
This is important because using current voltage can damage the device.
or affects its performance.
So always check the datasheet before designing a circuit.
Now, output voltage swing.
This parameter tells us how far the output voltage can go.
Ideally, it should reach the supply voltage.
But in real OP-AMPs, this is not possible.
For the LM741 with plus minus 15 volt supply,
The output can reach about plus minus 14 volts.
so there is always a small limitation.
This is important when working with signals close to the limits. Now we are going to talk about max output current.
For this tells us how much current the OP-AMP can deliver.
For the LM741, it is about 25 milliamps,
If we demand more current, the output may distort.
or the device might be damaged.
So this parameter is important when driving loads. Now, input voltage range.
Also called common mode input range.
This defines the allowed input voltage values.
For the LM741, it is about plus minus 12 to plus minus 13 volts.
If we exceed this range, the OP-AMP may not work correctly.
This output may become unstable or saturate. Finally, temperature range.
This parameter defines where the OP-AMP can operate safely.
For the LM741, from minus 15 to 125 degrees Celsius.
And for the LM741C, from 0 to 70 degrees.
Temperature affects performance like offset and gain.
So it is very important in real applications.
Now we are going to move into a very important part of this video, the simulation section. Up to this point, we have discussed the theory, we have explained what is an operational amplifier is, and we have analyzed the main parameters of the LM741. But in engineering, understanding theory is not enough. It is also necessary to verify that theory matches real behavior, and this is exactly why we use simulations. Simulations allow us to recreate electronic circuits in a virtual environment. This means that we can test circuits without physically building them. This is very useful because it saves time, reduces cost, and helps us understand how a system behaves before implementing it in real life. In this case, we will use Multisim as our simulation tool. Multisim is widely used in electronics education because it is intuitive and powerful at the same time. With this software, we can place components, connect them, and observe signals using virtual instruments.
Now we will move on to the simulations. The goal of the simulation is to verify some of the parameters from the LM741 datasheet. And instead of only talking about theory, we will observe how the amplifiers behave in a real circuit. For this simulation, we're using Multisim to build and test our circuits, and we will analyze three important parameters. First, the gain, second, output voltage swing, and third, offset voltage. For each case, we will compare the simulation result with the values reported by the manufacturer. And this is going to help us understand how close real behavior is to theoretical expectations. Hi. So, for these first simulations, we analyzed the gain of the LM741 operational amplifier. We configured the circuit as an inverting amplifier, which is one of the most common configurations. And we use a 1 kilo ohm resistor for the input and a 10 kilo ohm resistor for the feedback. This gives us a theoretical gain of minus 10 according to the formula negative R2 over R1. And we apply a small sinodal input signal with an amplitude of 0.1 volts and a frequency of 60 Hz. On the oscilloscope, we can observe both the input and the signal, the input signal and the output signal. Input is red, output is yellow. So, we can clearly see that the output is inverted and significantly large, and the amplitude of the output is approximately 10 times greater than the input signal. This confirms that the circuit is working as expected and that the LM741 provides the required gain. And this also shows us how we can control amplification using external resistors. Now we analyze the output voltage swing of the LM741. I forgot to mention earlier that the OP-AMP is powered by a dual power supply of plus minus 15 volts. For this simulation, we keep the same circuit configuration as the previous one. The only change is that we increase the amplitude of the input signal. So, we start with a small signal and gradually increase it to higher values. At first, the output signal increases normally and follows the expected amplification. However, as we continue increasing the input, we begin to notice distortion. The waveform starts to clip, which means the amplifier cannot increase the output anymore. We observe that the output voltage is limited to approximately plus minus 14 volts. And this happens because the OPAMP cannot reach the full voltage. These results match the values reported in the datasheet for the LM741, and this parameter is very important because it defines the usable output range of the amplifier. So, as we can see in the screen, if we put the input on 16 volts, it is not working anymore. In this final simulation, we analyze the input offset voltage of the LM741. To do this, we remove the input signal and set the input to 0 volts. In an ideal operational amplifier, the output should also be exactly 0. However, when we observe the output, we notice a small voltage. This small deviation is also known as the offset voltage. It is caused by internal imperfection in the transistor inside the operational amplifier. And even though the value is very small, it can affect precision circuits, especially in sensitive application. The value we observe is consistent with the datasheet, which it specifies a small offset in the millivolt range. This demonstrates that real devices are not ideal and will always introduce small errors. And understanding these effects is essential for accurate circuit design.
Now we have reached the final part of this video. In this lesson, we explored the operational amplifier and specifically the LM741. We understood how it works as a differential amplifier and why it's so important in analog electronics. We analyzed key parameters such as offset, gain, SEM-RR, PSRR, and output limits, which help us understand the real behavior of the device. We also use simulations to verify these concepts and connect theory with practice. The LM741 remains a valuable tool for learning because it clearly shows how real OPAMPs behave. Understanding this device builds a strong foundation for more advanced electronic design. Thank you for watching. See you in the next video.